Okay, so that brings us to an end of the first half of my talk. Are there any other questions about the MapReduce paradigm mentioned?
How many map tasks or reduced tasks should be there for optimal performance?
So actually, that's a good question, and there is no real simple answer for that. It depends quite a bit on how large your cluster is, first of all. In addition, it also depends on application characteristics. So what is the, for example, what is the ratio of the computation that it's doing compared to how much I/O it may have? So it differs a lot between applications. There are some rules of thumbs that people use. For example, typically the number of reducers that are used is about the same as the number of machines you have, so that you can extract X amount of parallelism, etc. But a lot of it has to do with empirical fine-tuning of it.
We have a question, Princeton.
Yes.
So if you go to the word count example, can you talk a little bit more about the sort and shuffle step right after the map? And my question is specifically around, take for example the word fox. Why was that not sent over to the other reducer? I mean, is it at that point you are trying to figure out which data should be sent to what reducer?
Yeah, so after the map functions finish, you basically sort the intermediate keys, and then you assign one reducer to each key. So in this example, for instance, all the instances of the word fox will be sent to one of the reducers. So in this case, you're sending that to the orange reducer. So that is a requirement of the programming model itself, that all the reducers basically take each intermediate key and all the corresponding values and then combine these values together. So yes, the partitioning is happening after the maps get done.
And who is doing that sorting?
Thank you.
So it's the framework which is basically doing the sorting. So it's transparent to the programmer, but it is being done by another line.
The question at UCLA.
Sorry. My questions had to do with the transformation of a problem into a MapReduce operation. Are there real-world problems that are more difficult or perhaps even impossible to transform into something that can be solved in this way?
Yes, certainly. And so MapReduce clearly is not really a solution for all kinds of problems you have. It is a reasonably simple data model that programming model that you can transform some applications into. For some others, and particularly there is work going on even here at Indiana University about iterative algorithms, things that may be used in, for example, data mining or graph algorithms, where you may have large graph structures or large matrices, and you need to iterate over these quite a bit. And MapReduce actually is pretty bad for some of these kinds of operations, particularly because it assumes that you have this linear workflow and data is going from mappers to reducers and then you get the output. But quite often you may actually have more complex workflow structures. You may have tags instead of this kind of linear model, or you may have multiple iterations. So you may have cycles in your computation as well. So for these kinds of applications, MapReduce is actually not very good.
Question from UCLA.
Yes.
The question is, since Hadoop is written in Java, one of the side effects we are seeing on our cluster is that after the users run the job, it leaves sometimes a lot of leftover Java threads, and the stop PFS command doesn't actually clean it up. One has to explicitly go to that node and clean it up. I don't know whether it's something specific to our cluster, or is it because of the Java, or is there any plan to write Hadoop in C or some other language?
So I'm not sure if I may be able to answer the specific question or the problem that you're facing. From what I understand, I don't think there's any plans to implement Hadoop in C, but it does provide plugins so that you can plug in native code into your execution. So if you have your map and reduce functions written in C or some other language like say Perl, etc., you can plug that into the group execution. So it does provide the capability to do that right now. All right, so now I'll move on to the second half of my talk. First of all, what do I mean by a traditional MapReduce environment? Typically, MapReduce is executed on tightly coupled clusters where you have mostly large number of homogeneous machines which are connected over some sort of a switched local area network, which may be Ethernet or some other form of reasonably fast and high bandwidth network. And the assumption is that you have these compute nodes which are dedicated to you, and data is already available inside the cluster, and the data has been chunked up and pre-placed on all these machines before you start the execution. Now, this assumption may not hold true in many different environments and domains. In particular, the sources of data themselves may be geographically distributed. Examples of these include cases where you are generating scientific data which is spread around the globe. This may be coming from scientific instruments and sensors such as oceanic or atmospheric data that you are using to feed weather applications or climate applications. Also, a lot of data that is being generated in the public and social domain is being generated inherently in a distributed manner. For example, a lot of data that is generated by users themselves, such as user blogs, or data that is being generated, say, in different parts of the city from your traffic grid. A lot of commercial data actually is distributed inherently. This corresponds to both the brick and mortar kind of operations, where different warehouses are generating a lot of data every day based on the sales that they are making, as well as e-commerce data, which may again be distributed in different data centers around the globe. You may also want to collect a lot of data from different sites in order to be able to analyze the user behavior and health of the system. And an example of this is our CDNs, which have servers placed close to the users, and they generate large number of queries every day and large number of requests, and they need to combine all of this data to figure out what the health of the overall system is. And finally, as the mobile systems become more and more capable, now users themselves are becoming distributed and mobile generators of data. All of us are actually fairly sophisticated sensors by ourselves because we have these camera phones. We have other kinds of sensors in our phones these days, both environmental sensors like temperature sensors, as well as GPS devices, etc. So there's a lot of data which is being generated in this kind of an inherently distributed manner. In addition, even if you have data which is centrally located, you may still want to combine multiple data sources. An example of that is how do you trace epidemics in real time. So one way to do that is to combine data from Google Maps with data from CDC or Center of Disease Control. So as you see more outbreaks happening, you somehow want to figure out the progression of this disease. So you may have to actually tap into multiple data sources in order to be able to do that. In addition, besides the data, your computation resources themselves may be distributed. An example of this is the fact that a lot of the data centers and clouds are now geographically distributed themselves. So think of Amazon EC2 regions. Some of the regions are in North America, some of them are in Europe, Asia, etc. I mentioned CDNs as another example. So Akamai, for example, has large number of servers which are locally located close to the users. And these again have a lot of state and logs that they need to combine and look at. You have computational grids. An example is the Future Grid, which you heard about yesterday. And in addition, you also have volunteer computing platforms such as Boeing for at-home projects, which combine resources which are highly geographically distributed into a single computational platform. So overall, if you have these distributed data sources and distributed compute resources, the question that we are trying to look at is, now how do you combine this data in a meaningful manner, and in particular, how do you execute MapReduce in this kind of a highly distributed environment?